Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. So let's get moving. Bam! So today we are talking about a titration example number 1. This is a very long problem and I'm going to have to break this particular video into 3 different videos here to do just this one problem. So here's the first part. We're going to do a weak acid titration with a strong base. Okay, so the first thing that we're going to do on all these titrations here is that we're going to use a graphic. Okay, and I want you to notice something with this graphic. On the y-axis we have pH, and since it's a weak acid that's being titrated with a base over time, the weak acid is a pH that is low, that is less than 7 initially, and so you should see in this graphic, we have a pH around approximately 3 if you look at that graphic, and that is before we have added any base. As we add base, which is along the x-axis, the volume of base that is added, you should see that the pH slowly increases over addition of base. That should make sense for you. This is where and how we get this graphic. Okay, so at this area or region, before we hit the equivalence point, this is the buffer region. And notice that the pH does not change very much even with addition of base. Okay, so that is a buffer. So remember, buffers snarf up or consume hydrogen or hydroxide ions. In this particular case, the base is being consumed by the weak acid, and therefore the pH is not changing very much, and that's why this is relatively flat within this buffer region. Okay, so 3 calculations in which we're going to do. Number 1, we're going to do a before titration begins calculation. That is the pH initially, and we're going to be using an ice table based solely on the weak acid itself. Okay, then the second calculation that is very common is the halfway or the midway point. Okay, and the concept that we're going to follow with this is the concentration of the conjugate pairs are equal. That will actually drive the math in this particular problem. Okay, the half of the volume of the equivalence point is required at this point in time. Mathematically, the pH is equal to the pKa. I'm going to show you how all that is derived by doing a calculation, and that will make sense. So go back to this graphic here after we do this entire problem, and it will make sense. Okay, I'm going to go over why this is 12.5 milliliters here in just a second here, but I do need to do one other part. Okay, and that is the equivalence point. The equivalence point is when the moles of the acid is equal to the moles of the base. That quotation section right there is going to be driving the math, deriving the equivalence point, or what we call the end point of the titration. We're going to write a new equation. We're going to switch the K. We're going to do a nice new ice table. And notice here that since the base is strong, then therefore the pH is going to be greater than 7. This is also the inflection point of the graph, and that's where this slope changes from one side to the other, if you will. Okay? And this particular problem, in example number 1, we are going to have a volume of 25 milliliters of base that is required or necessary at the equivalence point. Notice that I already did the halfway or the midway point volume at 12.5 mils, because of course that is half the volume of the equivalence point. All right, so hopefully you understand that graphic. That graphic is going to be very important. You should also see that with this graphic, the pH before titration begins, okay, the pH is acidic. The pH at the halfway or the midway point is acidic. The pH at the equivalence point is basic, okay? And this applies to a weak acid titrated with a strong base type of calculation. All the graphs will look the same if it's a weak acid and a strong base. All right, so another thing that we need to know is indicators for titrations, and the indicator is necessary at the equivalence point or the end point of the titration. So it's a colorimetric indicator is used to indicate where that change occurs. Okay, and it should be near the equivalence point or the end point of that titration. So here's a chart showing a variety of different indicators, colorimetric indicators, that change different colors at different pHs. Notice that this ranges from pH of 0 all the way to 14, so it goes through the entire pH range. Sometimes a universal indicator is used, and that is a colorimetric indicator that is a combination of a variety of the different ones of these that will change pH, will change color and of corresponding to the different pH. Okay, sometimes you can use a liquid universal indicator, and sometimes you can use a paper indicator. Okay, the best indicator of choice is when the pKa of the indicator is equal to the pH at the equivalence point. And I'm going to rewrite this here mathematically here. The pH at the equivalence point is equal to the pH of the indicator. That's very important. Okay, so here's an example of what I've done in the lab here. What I have is a titration. Before the titration has begun, I have a weak acid inside the Erlenmeyer flask, and I am titrating with a strong base inside that burette right there. Notice that the color of the solution is colorless to begin with on the far left hand side, and over time as I add base, because I've added a colorimetric indicator, and in this case I've added phenolphthalein, it changes from colorless to a pink or a fuchsia color. That complete conversion is when the conversion has been changed all the way to a basic solution, and that is beyond 8 to 8.5 for phenolphthalein, and it changes that fuchsia color that's on the right hand side. That is a colorimetric indicator. The best way to do a titration, however, is to use a pH meter. A pH meter is the best way, but the colorimetric indicators are excellent approximations as well. All right, so let's continue on with this problem here. So titration example number 1, we're going to do a weak acid titrated with a strong base. So here's our problem. 100 mils of a 0.025 molar benzoic acid, that is C6H5COOH. I have the equation, or not really the equation, but the graphic of what that equals in the upper left-hand corner, okay, drawing out benzoic acid for you. This benzoic acid solution is going to be titrated with a 0.100 molar sodium hydroxide standard solution. The sodium hydroxide is the strong base, the benzoic acid is the weak acid. Okay, so what is the pH before the titration begins? That's the first question that we're going to answer. The second question that we're going to answer is what is the pH at the halfway or the midway point? The third question that we're going to answer is what is the pH at the equivalence point or the end point? These are the three most important questions to answer in any pH titration example. Okay, so one thing that you probably have to do is you have to look this up in the back of your textbook in a table in one of the appendices, or maybe it's given to you. And you would have to be given the acid dissociation constant for the weak acid. In this case, it's benzoic acid. It's 6.25 times 10 negative 5 for benzoic acid. Notice that exponent is negative, therefore that Ka value is less than 1. Therefore, benzoic acid is a weak acid and reactant favored. That should hopefully make sense to you going back to the equilibrium unit. Okay? All right, so here are the steps that we're going to be following for this pH titration and this pH titration. So number 1, before titration, we're going to be doing an ice table. We haven't added any base, so we don't have to worry about the base. We're going to do just the benzoic acid and do an ice table based solely on the benzoic acid. The next example is the halfway or the midway point. Okay, and at the halfway or the midway point, we're going to write an equation. In fact, that equation is going to be the same as the pH initially or before titration began. But we need to know conceptually what's happening, and that concept is the concentration of the conjugate pairs are equal. Okay, and if that is the case, then mathematically what we have is the pH is equal to the pKa. All right, those are two very easy calculations. The third calculation at the equivalence point or the end point is a little bit more difficult. And this is all based on the moles of the acid is equal to the moles of the base. So we're going to have to first calculate the moles of the acid. Then we're going to have to calculate the moles of the base. They actually happen to be the same value. Okay, we're going to calculate the total volume, and that is the volume of the acid that we have in the flask plus the added volume of the base that is required to reach the equivalence point. And then we're going to calculate the concentration of the conjugate base of the weak acid that we had. And this concentration is going to be based on the moles of the acid converting to the moles of the base, the conjugate base, and the new volume, the total volume that it is in. Then we're going to write the new equation, which is going to be a switch. We're going to derive the new K because that's also going to be a switch. And then we're going to set up an ice table based on this and perform that necessary calculation. All right, we should be making some predictions as to what the pHs are. And I alluded to this already with the graphic that we did before. But before the titration begins, what's the pH? Well, it's a weak acid, and we haven't added any base, so it better be acidic. Okay? And then at the halfway or the midway point, we've only added half of the volume necessary for the equivalence point of the strong base. And you should go back to that graphic, and you should see that that graphic is indicating that we are still in the buffer region. And that buffer region is most certainly acidic. So the pH is going to be less than 7. Now, at the equivalence point or the end point of the titration, that is when the moles of acid are equal to the moles of base. Now, the moles of base are the strong base, so therefore it will overwhelm the moles of acid, if you will, to a certain extent. So therefore, that's when that switch occurs, or just prior to that point is when the switch occurs and the pH will be greater than 7. So you need to make these 3 predictions based on the graphic of which you have drawn for every single titration. And once you know those predictions, then deriving it mathematically, you should think, does my prediction correspond to what I derived mathematically? That would be very important. All right, so let's start off with this first calculation. So before titration begins calculation, let's do that. So we're going to use an ice table to determine the pH based solely on the benzoic acid. Since we haven't added any sodium hydroxide, that's the strong base at this point in time. Now we need to write the equation. So this is benzoic acid, and hopefully remember back to the equilibrium unit, and then back to the beginning of this unit of writing the conjugate pairs. Okay, so I got benzoic acid plus water. Now I'm going to write the conjugate pair of benzoic acid and the conjugate pair for water. Now since this is an acid, it will release a hydrogen ion. That hydrogen ion is going to combine with the water to form a hydronium ion, and then the benzoate ion will be left. And that's why we get our products right there. It's very important that you're able to derive the products. Remember, conjugate pairs are plus or minus a hydrogen. Since this is an acid, it will release hydronium ions in solution. That's why we have hydronium ions on the product side. Okay, this is our equation. Okay, we're going to do an ice table. That is initial, change, and equilibrium concentrations. So what is the initial concentration of the benzoic acid? That was 0.025 molar. Now I've highlighted the water in blue, not because water is blue, but just highlighted in blue. And it highlighted in as a liquid state of matter. So what matters about the liquid state? Well, solids and liquids are not included in K expression, so therefore I can ignore the water. Now, when we go back to that equilibrium unit, you should know how much you have initially on the product side for almost every single equilibrium reaction. And that would be 0 for any product, okay? That's how I'm coming up with zeros for the products. Now, this is an equilibrium reaction. This is going to shift from the reactants towards the products. Therefore, I'm going to decrease the reactants and increase the products. And I'm going to use the stoichiometric coefficients on the balanced equation to write those stoichiometric coefficients that I will have in this change section. So it's a minus 1x for the benzoic acid. I'm going to skip the water. And it's a plus 1x for the benzoate ion and a plus 1x for hydronium ion. Now I'm going to add up the initial and the change to get the equilibrium on this. So that's 0.025 minus x, skip the water, and we got an x for the benzoate ion and an x for hydronium ion. Now I've done my ice table. Now I'm going to write the Ka expression. Remember, Kas are products over reactants with the stoichiometric coefficients as exponents. Solids and liquids, and I do have a liquid, are not included in K expressions, so I should have Ka is equal to the benzoate ion times hydronium ion divided by benzoic acid. Okay? Now, I'm going to plug in these equilibrium values into that Ka expression. So the Ka was given to me in this problem, and that is 6.25 times 10 to the negative 5. I'm going to have x times x, that's x squared in the numerator. My denominator term for the benzoic acid is 0.025 minus x. I need to ask myself this, and this is coming back to that equilibrium unit. If 100 times the K if that is less than the initial concentration, then we're going to use the approximation and not the quadratic equation. So therefore, 100 times 6.25 times 10 negative 5, is that less than 0.025? Yes, that is. If that is the case, we're going to get rid of this minus x term, and we do not have to use the quadratic. Now what we're going to do is we're going to solve for x. We're going to take the Ka times 0.025, take the square root of that, and I'm going to get x, and here's x. Now, I'm going to go back to my equilibrium, okay, that I have on my ice table and find out what does x equal. X equals the benzoate ion concentration and also the hydronium ion concentration, and that's really what I'm interested in. So the hydronium ion concentration is equal to 1.3 times 10 to the negative 3 molar. Now from this, I should be able to get the pH. pH is equal to the negative log of hydronium ion concentration. I've plugged that in here. Now I'm going to put this into my calculator, and I'm going to get the pH. The pH is equal to 2.89. I've got 2 decimal places. I'm going to ask myself, is this pH reasonable? That is, this is a benzoic acid. It's an acid. Before titration begins, I haven't added any base, so most certainly I would expect that this to be acidic, as I predicted from the graphic that I drew previously. Okay, hopefully that is making sense for you. Okay, that is part A of this 3-part series in this video. I do most certainly have a crazy hat. Okay, give me a thumbs up if you like that video, subscribe to my YouTube channel, donate please, get a sticker or a t-shirt, and then you're going to be set. I'll see you for next time for part B, C for this problem. See you later. Bye for now.